Hello, and welcome to our first video. Before we get too far into the mathematical content of this class, I thought it would be useful for us to take a detour and talk about how mathematicians use language differently than other subjects. Mathematicians use language in a particular way. Because we want everyone to agree on whether a statement or an equation is true or false, we are very, very careful with the words that we use. We're so careful that we carefully craft definitions of mathematical words, concepts, and symbols so that we can avoid ambiguity, so that we can make sure that everybody is on the same page, everybody has a common knowledge base, and everybody knows what everybody else is talking about. Let's talk about definitions by using a silly example. Suppose you're going along, you're reading your math book, and it gives the following definition. A splorg is a tallywig that is flurf and zoop. Putting aside the nonsensical words here, we would know some things about these four crazy words. We would know a splorg is a type of tallywig. So if your object is not a tallywig, then it can't possibly be a splorg. What else do we know? Well, let's say we have a tallywig, and we wanted to show that it was a splorg. You see from the definition, you only need to check two things. Is it flurf and is it zoop? If both of those two things are true, it is a splorg. In fact, it must be a splorg. That's the definition of what a splorg is. But if our object is not one of those two things, if it's not flurf, then by definition, it is not a splorg. Now, even though these names have been completely made up, sometimes when we're reading our math textbook, it sometimes feels like the language is made up as well. But there is one thing of which you can be sure. In order to know whether your object is a splorg, you have to know what a tallywig is, you have to know what flurf means, and you have to know what zoop means. So, in math, definitions build on top of definitions, on top of definitions, and on top of definitions. Okay, so now let's come back to the mathematical world and talk about an actual example involving a definition. A prime number is an integer that is greater than 1 and whose only positive divisors are 1 in itself. If you look at the structure of this sentence, it's very similar to the one on the previous page. We have an object that's being defined. It's of a certain type, and it has a couple of restrictions to what it is. And just like on the previous page, in order to make sense of this definition, we would need to know the definitions of these three things. We would need to know what an integer is. Remember, that's the same as a whole number, something that doesn't have a decimal or fractional part. We have to know what it means to be greater than 1. I'm going to assume that we all know that. And we have to know what a divisor is. Remember, an integer a is a divisor of b if b over a is an integer. Armed with this knowledge, we can figure out when a number is a prime number. Is 5/2 a prime number? Well, a prime number has to be an integer. 5/2 is not an integer, so it cannot be a prime number. Is 18 a prime number? 2 is a positive divisor of 18, because if we take 18 and divide by 2, we get an integer. So 18 is not a prime number. Is 17 a prime number? Well, yes, 17 is an integer, and 17 is greater than 1, and the only positive divisors of 17 are 1 and 17, so ding, 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 17 is a prime number. Now, in this course, we're going to see a lot of new definitions. There'll be definitions in each of the different topics that we'll see. One of the tools for really mastering the concepts in this class, and really in any math class and in future computer science classes, will be to deeply understand the concepts that we're defining. When any mathematician is trying to understand a new concept, they will do the following things. They will write down the precise definition given in the book, the lecture, the article that they're reading. They'll try to understand and digest the definition and restate it in their own words. They will find some examples, things that satisfy the definition. And they will find some non-examples. They will find things that do not satisfy the definition. All of this time that you're investing in understanding a definition is extremely worthwhile. Until you understand the definition inside and out, there's no way to use it or answer any questions related to it. So I call this the definition exercise. When you have a new term, you write down these 4 steps and put that in your notebook, and that will help you as you're going forward. So let's say we wanted to do the definition exercise for the word prime. Well, we have a precise definition. If we go back, we see a prime number is an integer that is greater than 1 and whose only positive divisors are 1 in itself. That's copied directly from an earlier slide. Now we need to put that into our own words. A prime number is a number that can't be broken down into smaller factors. Then we come up with some examples. So 2, 3, 5, 7, 11, 13, all of those numbers, they only have 1 in itself as a factor. And then often it's the most helpful to think about some non-examples. What are some things that do not satisfy the definition? 1 is not prime, negative 11 is not prime. Those are both true because the integer has to be greater than 1. Pi is not prime because it's not an integer. And 18 is not prime because 18 has positive divisors that are not 1 or 18. And a pro tip is that you should look for examples that show that you understand the intricacies of why an object doesn't qualify under the definition. So whenever you see a new term, use these tools to get a deeper understanding of what that term means so that you'll have a stronger foundation going forward. That's it for now. See you in the next video.